Hello, everybody. How are you doing? Okay, I'm good, thank you. So we are gonna do the next lab today. Let me double check my audio. Okay, just want to make sure that we got sound. And let's caption. Okay. So for today, we are gonna do the next lab in LC-3, which is gonna be lab 3. Let me share screen. So as we learned the process last time, we are able to use the online simulator, or if you're using a Windows PC, you're able to build your program. So make sure that we open those things. And then for those of you who are using Mac OS or online simulator, you can use one of the text editor, like if you have Visual Studio Code or Sublime, those things you need to open it to write your code. And again, I'm using Windows PC, so I'm going to demo everything from the regular LC-3 editor and simulator that's supplied by the textbook or the publisher company. So to start, let's talk about the lab. And today we are going to work a little bit more with data movement and also some operation as far as arithmetic. We're going to spend a couple of weeks working on arithmetic in assembly. And then we'll move forward to do a little bit more complex program down the line. So in this lab, we are going to do some simple exercises. The first one is going to be on arithmetic instructions. And in this program, what we're doing is we're going to use two variables, P and Q. And we're simply going to take P minus Q, right? And we're going to set the value on the simulator. And I'll show you how you can do that. So don't forget that you are going to be required to provide screen capture and then answer these questions when you put together your lab document. So you can add it to the existing document, or you can create another document, put down the questions, the answer, and the screenshots. So you can upload that for grading. And I'm still working on the rest of the lab grades. I'll get that done this evening or tomorrow. So to start, let's take a look at this program. And what I'm going to do is I'm going to show you in my editor. Okay. And so here's my editor. I have the origination address at hex 3000. And what we're doing here is we are going to load the label P, which is at a location or an address in the memory. So in this case, what we can do is we can do an indirect load, which is going to be LDI. And we'll talk about that more in the next session. So LDI allows you to point to the location of P, which is here. And we're going to link that location to register 3, R3. Okay. So the address of P is going to be linked to register 3. And then we are going to do the next load, we're going to load the label Q to register 4. And know that this program is not going to output into the console. You are going to strictly use the simulator to check your value. Okay. So what we did was we basically declare what P is and what Q is, right? And point to the address where they would store the value. So it's kind of like in C++ where you say int P equal, and at this point we didn't initialize anything. So you just say int P semicolon and then int Q semicolon. So that's what we're doing here. And then what we're going to do next is we are going to set up the 2's complement. And this is how we're going to operate 2's complement for subtraction. So what I want is I want to have P minus Q. And I know that Q is at register 4, the address of it anyway. So what I'm going to do is I'm going to do the 1's complement of R4 by not it and store it in register 2. So when it flipped the bits in register 4, it's going to store the result in register 2. I can reuse register 4, but what I want is I want to show you that you can use another register. Okay, if you want to reuse register 4, you can. But in this case, we're using register 2 to store the 1's complement of Q. Then it is not completely negative or subtraction until we do the 2's complement. So we have to take the result of the not, which is in register 2, and we're going to add decimal 1 to it. You can add a hex 1 or a decimal 1, it is the same. So I would take register 2, add it with 1, and put it back into register 2. So the result at this point, the 2's complement is going to be at register 2. So it is negative R4 in register 2, and that's equivalent to negative Q. Any question with this?
Yeah, I had a question.
Sure.
So when you do the 1's complement, and you're using this register 2, let's say like you were saying you use register 4, now you're just replacing what register 4 was with the 1's complement now? Is that what's happening if you were to use the register 4 again?
Yeah, so if I use register 4, it'll look like this.
Okay.
So I flip the bits on the register 4, which contains the address, or the address that's point to Q. So when I do the not on that, I store it back onto register 4. That's the 1 complement. And then for the 2's complement, I take the not and add it with the 1. So
Okay,
yeah, the not is here, right? Add it with the 1 and then put it back on register 4. So that means that I'm going to change this up so you can follow. The reason why I use R2 is it's less confusing, right? Because I say, oh, R4 is equal to negative R4. Sometimes that can be confusing to people. But if you're reusing the register, it will say not R4, R4. So it's going to not whatever that's in register 4, which is Q, and then add the 1 to it, which is make it a 2 complement, and put it back into R4. So you can do it that way.
and then it can only have 1 label for each register, right?
And then here you have to do this, right? Yes. You're gonna load 1 label to each of the register. You cannot reuse. So if I use R4 here, I cannot reuse it for the next one because it's tied to an address. And you don't want to have one or 2 labels to 1 register because it's only able to store one piece of information at a time for 1 word. So I'm going to put it back to the 2 so that way it doesn't confuse other people who just joined. But you can use any register, really, right? So we talked about at this point, it is negative Q because we took the 2 complement of Q, which is R4, and we store that onto register 2. Or we add that with a 1, so that way at register 2, it would be negative Q. And so your equation is P minus Q. So we want to find the result of P, whatever P could be, and whatever Q could be. So I need to make sure that I store the output. So here at this point, my result is going to be, my destination register is going to be register 1. Okay, register 1. And I have Q at register 2, or negative Q, as a matter of fact, added with P, which is at register 3. Okay, so P minus Q is going to put the result in register 1. And so at this point, I want to take that value and I want to store it to a label called minus. Because what you don't want is you don't want the value to stay in the register. Remember what I said before, that register is going to be temporarily storing. So you want to take what's in the temporary storage and put it to an actual memory location where you would have an address, which is this. Okay, so P has an address, Q has an address, and its output minus has an address. Okay, so once I have the result of P minus Q, I want to store that out to a location so I can see the value, which is called minus. And I wanted to fill that with an address. And at that, after that point, we are going to stop the program, halt. And don't forget that at the beginning, you have to have the origination address where your program starts. So it's going to be .org. Now, unlike the last few programs that you saw, we really use the data section to fill values. In this program, what we're doing is we're filling it with the actual address for our label. So think of this as variables, right? When you create or declare your variable in your program, the compiler actually tied that to a memory location. So we manually do that here. P, since we load it to a register to handle the arithmetic calculation, we need to start it with a certain address. And I recommend that you use sequential or closed address, so that way you don't have to go up and down the simulator to find a value. Okay? So if I have P, I can fill it at 3120. Why can't I make it closer to this? Well, because each of this line is going to take up a word. Depending on how long your code is, you want to give it a little space before you started filling. Because if your program is very long, let's say your program is 200 lines, you want to be a little bit further down. So I would probably want to go down to like 3,200 or 3,300 or something like that. Okay, so we want to be a little bit further down on the memory to be able to look at our label and our output. So here we're going to fill P with hex 3120, and this is a location on the simulator, an address where P is going to initialize, and we can set a value to it. Okay, like I can give P like hex 5, and I can give Q like hex 3. 5 minus 3 should be 2, right? And 2 is going to be put here. And then after that, don't forget to put the dot N. So once I have my program, and for those of you who are using the Windows version of the simulator and the editor, you can assemble your program. And then for those of you who are using the online one, I showed this last time, right? You need to copy and so click open assembler and then copy and paste your code in because it doesn't allow you to automatically assemble through the website. So you got to add the code in there so that way it can be assembled. Okay, so once you click assemble, check to make sure that there's no error. You should have a couple passes or it shouldn't give you any kind of red error on the online simulator. Then for me, I'm using the simulator on my PC. I can open up my simulator and I'm going to go ahead and load my object file. Okay, but before you run, I need to show you how to do this. So here's my simulator, right? I open the file, I load it, but I don't want to click run. So what I want to do is I want to go ahead and set the value. And you're going to click the set value button. Remember that I need to set the value for P and Q to test my program. So let's say that I give P 5 and Q 3, right? I should have 2 as an output. Always use hexadecimal value in your simulator. So at the location, I know that I fill P at 3120. So I need to put down hex 3120 for the location of P. And then I put in the value hex 5. Again, right? Click set value. In here, go to your fill and look at your address. Put that in, hex 3120. And then put down the value you want to set for P. Then apply. Then we want to set the value for Q, and we need to do this before we run the program. So to set the value for Q, we go to the next address, so hex 3121, and I want to set this for hex 3. So 5 minus 3, that's easy. You can calculate that in your head to check, right? Apply. So we need to set the value for both of these, and then you click OK, and then you run. So now how do I know whether it has the correct result, right? I'm going to go to the jump to section here, and I want to put in hex 3122.
Set value part again.
I'm sorry?
Can you show how you got the set value menu?
Yeah. So you click this,
Okay.
the purple button or the 1011, and then you put in your P and Q fill location. This is before you run, okay? And then the value, for example. So once you had set that, you want to jump to the after you run the program, you're going to jump to the location. So here, as you can see, that I set for my 5, right? And I set my value for 3. But it tells me that I get a hex 5. So that means I need to go back and check my program. Is it operating the minus properly? Okay, because I changed some things earlier. R2, R3, R2, R1, star minus. So I want you to go and check to see the value that you set, 5 minus 3, right? And you can also open your calculator to check your arithmetic. Go to programmer. So if I have a hex 5 minus a hex 3, right, I should get a hex 2, but my program is showing me the hex 5, possibly because, you know, then I want to reinitialize my machine again, double check if I load the program properly. So you have to check 2 areas, either your code or, you know, how you set your value or how your program is ran. So I'm going to go ahead and set the value. X3120, X5, apply, 21, X3, apply, click OK, click run. Then we're going to jump to. Okay, so it's showing 5 again. So that means I have to go and check my code now. Okay, let me double check. R2, P, Q.
This is the R4 register that you're gonna put for the NOT.
No, because I'm reusing R2, but I can do that. Let's try that. That's right. Thank you for catching that. I see what you said. I modified my program earlier and I changed it. That's why it's giving me an error. Okay, so let's reload it. So every time that you reload it, just reinitialize your machine. And then go here, set my value. So once we check our code, we see that the wrong register was used. And then click OK, run the program, and then you're going to jump to. And so I have the right result. Yeah, thank you, Chris. I also caught that too. Okay, so we see the result in 3122, which is the minus label. So that's what you do when you test it without using the in and the out or the pseudo instruction, is to go to the actual address that you fill, okay, and then be able to check your result. So when you work on this lab, right, the process would be that you write the code, you assemble, you simulate your program. But before you run the program, you need to set the values for P and Q, and then run and go to minus, which is at hex 3122 to check your output. If it outputs correctly, then your code is done right. If it outputs wrong, then you check your arithmetic. Okay. Like earlier, you saw that I had replaced the register through the explanation and I forgot to change it back. So for the answer, we already know we can go to the fill section to look for P and Q. So for P, it's at this address, right? That's where we jump to or we set. For Q, it's at the adjacent address, which is right below it. So on the simulator, when you jump to this, right, this is my P. I set it for 5. And then I look right below it. I set it for 3. 5 minus 3. I should have a 2. That's at this fill. And when I copy this, I didn't tap it out, but you can tap it out to make it look all aligned and nice and neat. So just make alignment is easier for you to check the code down the line. So you can just, this is a very basic program. So, all right. Any question?
Yeah, so when you set the value, you're using hexadecimal, right?
Yes, because on the simulator, it's designed for hex. So as you can see, they already put the little X there for you, right? So if you look at the column on the simulator, so on the website, it's a little bit clearer, but here, right, this is the address column. This is the value column, okay? And this is the binary equivalent. So when you look at the binary value, you should see that that's a 2, that's a 3, and that's a 5, right? We spend a lot of time during the first week doing the conversion, so that way you can see quickly what that would look like in binary as well. Now you notice that for register 3, how it shows like 5 and then -3. But don't always rely on this. In this program, it shows this, right? But in a more complex program, you're gonna keep reusing registers. So sometimes your value is not exactly like how you for the last step, it's not exactly how it's supposed to be. But what you want is you want to store it out to an address. So I have the value as the output, and then I store it out so I can see it. See a chat. Can you show how to input value on the website? Okay, so let's see. Let me get to the link. I wonder if it's gonna let you put the object file in. Let me try it. Yeah, so if for those of you who already use the Windows one, you can actually put the object file in, and it should be able to process it without having the extra step. But for the others, right, if you haven't assembled the program, you would then need to drop your file in here and then paste the code. It's an extra step. So, because it accepts the object file, right? So you're gonna see something like this, open assembler, and then you're gonna go to your editor, paste your code, and then assemble, and then load to simulator. Let me see on clear next, this one. Enter the decimal value for up and down. I think you can click it. Okay, so go down to, you can go to you can jump to it too. So all the way down to your 31. Let me see if I can, yeah, jump to hex 3120. So once you have your program assembled, right, you go here, you type in the address, and then you put in the hex value. Let me see. Yeah, you put in a 5 and then click the check, and then at 3120 you click here and then you put in a 3, you click a check, and then after that you're going to click run, and then you jump to it to see your result, which is here. Let me jump back a couple. Okay. So click the drop file in, add the code, assemble, and then you're going to search for the address. Once you get to the address, you click on the hex value here and then type in the hex value. And then the next address for the queue, and then you click run, and then go back and type in the address where you want to find your result, which is this guy right here. Okay. And then so I have the output 2. Explain C and D. Sure. Everybody got that for the website? Okay. It's just a few more steps that you have to set the value, and it's good that you can search it so you don't have to click all the way down. Okay, so let's talk about C. So for C, it says, why is the LDI instruction used to load the P and Q? So remember when we talked in the lecture this week, what is load, right? Load is for reading, right? When you're using LDI, LD, or LDR, that's to go to a location in memory to read the data. So what we're saying is we have a label or an identifier. Think of this as a container. It exists at, we set it to be at this location. And so when you tell the assembler that you're going to load the P value, the P label to the register with the LDI right here, that means that it's going to go to the location of P, which is hex 3120, to read the data for register 3. And the same thing with Q. We said that Q is filled with this address, 3121. What that does is it's going to take this address and associate it with this label, right? When we fill. But then when we load it, what that means is we tell the assembler to go to this location, 3121, the address in the memory, to read the data for Q, for register 4. So it's going to go to this location, find whatever value you set. In my case, I set it as 3, hex 3. So it's going to read hex 3 for Q after it read hex 5 for P. And then after that, it operates the subtraction. And then when we store, what that does is it's going to take the value from register 1, which is the result from the subtraction, and it's going to write it to this location in the memory, hex 3122, under the minus label. So this is just a name that we give it for this address. And so once it has the result for the subtraction, it's going to write it to the minus location. And that's how we're able to see it, right? We're able to see the result here, and the same thing on your website. We see it here. Okay. So when you load is when it actually points to it. So yes. So it points to the address of that container, so that way it can read the data. When you store, it's going to write to the location of the label, so that way we can go there to check the output. Yeah, LDI is, we'll talk about what it's bypassing or what it's using in the next week, the actual mechanical part of it inside the processor, or the mechanism of it inside the processor in the next week. But I want you to be able to test it with the lab this week so you can understand. Question. Okay, so that's very basic. Make sure that we know the functionality. I already explained this STI. And then, yes.
So the STI reads whatever is at R1 and it stores it at the address?
Yes. So
Okay.
it takes the temporary storage value and it stores it to the permanent address that we fill
Okay, yeah.
Yeah, and then for the LDI, right, it loads the label or the data from the label from a location to the register so we can calculate. So it can operate the calculation. And then the register that you see in the last store, right? That's easy. If you look, we store from register 1 to minus. Okay. So STI is store indirect. I put the comment in my code here. So if you want to add the comment so you can reference it later, you can. So I put store R1 value to minus label, which is filled at hex 3122. Now, we do this because in our low-level program, we don't have a compiler to handle this, right? Like I said before, in the higher level language like C++, what you have is you have the compiler that does this for you. So when you declare a variable or a container, it automatically take that name and it ties it to an address for you. That's what's really happening when you do variable declaration or container declaration, you know, in C, C++, Java, etc. But in assembly, we have to manually create all of this because we don't have a compiler to be able to handle that for us. So that's why when you see assembly can be used to write compiler. It can also be used to write like browser, like your Chrome, so a lot of like the application that works directly on with the low level, you're gonna see that assembly is useful for that. Question. All right. So make sure we include our answer and our screenshot on our lab submission. So for 2, I didn't give you a screenshot for this because I want you to take what you got here and be able to build it for this one. So it's a little bit harder, not that much harder. So we want to make a program to perform the calculation. We have x is equal to y plus 1 minus z. And in this case, we have 3 variables, right, and a constant. So we have to bring them into the program, right? So it tells you that your x is at this location. That's going to be where we're going to be able to find the result. Your y and z can be in any of the memory location, but I would keep it right above this. So that way it's easy for me to check my program. Okay. Okay, give me 1 second. Let me see if I have typed it in Word so it's easier to see. Maybe not. Oh, I did do it. So I'm going to show you this in Microsoft Word because it's just bigger in font. Oh. No, sorry, that's a different program. Let's see. Well, I'm going to have to load the other one. Okay, so let's see. Hope you guys can see. Let me do this real quick. I'll put it in a bigger font for you. So I know it's really hard to see on Zoom windows. Okay, so I'll start with the top and I will work my way down as you type. Okay. So this is the second exercise. We are given a location for X and we need to include this equation into our program. Simply that. So I simply add the comments at the top so that way I don't have to flip back and forth on my documents or my editor. So I would have X is y plus 1 minus z. X is found at hex 3225. So we know that this is going to be one of the fill location. Y and Z can be at any memory location. So to start our program, we always start with origination address. So we would say .org hex 3000. That's where our program going to begin. And as I mentioned before, you don't have to do this, but it's always good to clear out the register I'm using. So basically, I'm using register 1 and register 2 right now. So I'm going to go ahead and clear that out. And the way that you clear it out is you AND it with a 0. So I use AND R1 with the 0 is going back to and store it back at R1. So when you do that, your register 1 is initialized at 0. And then for the second line, I'm going to do the same thing for register 2. I'm going to go ahead and clear it out and making sure that it doesn't have any kind of address or number inside it. I initialize it at 0. Then because my problem asks for equations, right, variable in the equation, I'm going to go ahead and load those just like the last one. So I chose to put Y, and I wanted to load that to register 1. And we are going to do an indirect load. So it's going to point to the location for Y. So I said loading indirect Y to register 1. And that's your label Y. And when you look at an equation like this, you are going to operate within the parentheses from the inside of the parentheses and outward. And we are going to work later on labs that are going to require more complex equations. So we want to make sure that we understand. So when you are given any kind of equation for programming, it's always a good practice to start within the priority of the calculation area, which is inside the parentheses here, right first. So what I want is I already clear Y and I loaded Y to register 1. So I'm going to use register 1 to handle what's next inside the parenthesis. So what I do here is I'm going to take Y, which is pointed to register 1, or register 1 pointed to Y. And then I'm going to add the decimal 1, which is this guy. Okay. So at this point, my register 1 is going to hold Y plus 1. And then after that, I'm going to move to the right because that's the next thing that I need to handle here for my equation is to subtract the Z. But you always want to approach this with Z as an absolute value and then handle the 2 complement. So I'm going to treat Z as a label and I need to load it to the register that I previously cleared, which is register 2. So I would take Z and then I'm going to load it to register 2 by doing an indirect load, just like the other one. So here I indirect load Z to register 2. And next, what I need to do is I need to get it to make it a subtraction. So after I load it to register 2, now I can do the 2's complement. So first, I'm going to do the 1's complement, which is I'm going to flip the bits or not it. So if Z is loaded to register 2, then I'm going to not register 2 and put it back into register 2. So One's complement register 2. And it's not a complete subtraction until I handle the 2's complement. So after I have not registered 2, then I would take it and add 1 to it. This is the decimal 1. You can use a hex 1, but I like to keep it decimal as the program calls it. So same value is going to be inserted. So you are going to use, you're going to add 1 here to register 2 to be able to have the 2's complement at register 2. So register 2 at this point is going to have minus z or negative z. And we want to put the equation together now. Here I'm reusing the register, but you're welcome to use other register to make it less confusing for yourself. So I decided that register 2 is going to store the output of y plus 1 minus z. So I know that negative z previously was in register 2, which I use here. And then I add it with y, y plus 1, which is in register 1. So y plus 1 subtract z and store the result into register 2. Now, if you use register 4, 5, or 3, that's fine. You just need to store it from that register to your X label. Any question? So after we have register 2 is the output of our equation, we're going to store that to the X, because recall that it is X is equal to y plus 1 minus z. We already have this part. So we're just going to tie the register that stored the output to X. So here we're going to store it from register 2 to the X label. And then we do a halt. And then our fill section is for the addresses. So for after the halt, I have X. The problem that you're given, use hex 3225. So that's the location for X. And then for Y, I chose to use the adjacent or the below address. So I use hex 3226. And then Z, I use hex 3227. And don't forget the .n. So let me move this up a little bit. So in case you're still typing. And you can give it space so it's easy for you to read the program. Like each, like this is the load section, this is the arithmetic section, there's a halt, but you can write it all together. It doesn't matter. As long as you can understand what it's doing. Any question?
Yeah, when you when you put for number 1, that's just decimal, right?
Yeah. So you can use hex here like this. It's the equivalent. I chose to use the integer 1 because the decimal 1, because just like following the equation for this and for this, but you can use either or, that's fine. Ultimately, it converts it to binary anyway. So it doesn't, a hex 1 is equal to a decimal 1. So, if it's a larger number, then we should use a hex, but in this case, 0 through 9, you can use any value that's equivalent, decimal or hex. Okay. Any question? Assembly is very step by step. right? You got to break it down to the sub-step and then you're going to build it from there. So just like what we talked about before, we went from inside of the parentheses and we worked outward. And then from there, right, so we're going to load all the label, make our variable, and then initialize them or treat them with arithmetic operation, like we have to handle subtraction, addition. And then once we have the result, we store it to a physical location in the memory so we can check it, right? And then so your fill section, your fill can either be values or it can be addresses. And always use hexadecimal here, okay? Because the way the system sees it, they're all like addresses anyway. Offsets.
So when we set the value, we can only use hexadecimal.
Yes, your fill, your data section is only in hexadecimal. But other steps you can use other. Later on, you're gonna start seeing that I would use hexadecimal more, but you can use decimal. Okay, everybody good with the code here? All right, so here's my program, right? Assemble your program. And then once you do that, you will go make sure that if you had the other program running before, reinitialize or clear out your machine. Or for those of you who are using the online simulator, just reopen the link. A new link or new tab. And then what you do is you just load your program. Okay, then once you load your program, you check everything, then you can set the value like what we did before. And in this case, you're going to start with Y and Z, which is at hex 3226 for Y. So let's say if we give Y is 1, and then for Z is the next one, X3227. Let's say if we give it another 1, and then we can click OK, and then we run the program. And then we are going to jump to X3225 to check. So I gave it a 1, right? 1 plus 1 is 2, subtract 1 is 1. In this one, I had given it, so you can use like 4 and 3 and 4 here, but it's just, I got lazy and I just used sequential addresses, right? So the results on top at 3225 right here. You can check it with other values, like you can test it. Now, when you get a negative number for the result, so for example, if I take Y is 1 plus 1 subtract 4, for example, right? You would see like the hex equivalent for that negative value. So it would say like F something at the 3225. So now we're able to create a program with 3 variables or labels, right, to handle arithmetic calculation. Yeah, same thing like what you did before. Okay, let me refresh. So you just get your program into here, click this, drag your file in here. Open assembler, take your code. Now, those of you who are using editor that doesn't translate well, if it's throwing errors because the symbol is not converting, right? Assemble, load into simulator, go to the address. So you're gonna jump to hex 3226, or let's do 225 right here. And we're gonna set it at the 6. So I'm gonna give it a hex 1. And then for the Z, let's give it a bigger value. Let's give it a 3. So 1 plus 1 is 2 minus 3. It should be a -1 over here, equivalent in hex, right? And then after I loaded I set the value for 3226 and 3227, I'm going to go ahead and click run. Then I jump back into this location, 3225, right? See? It's a negative value. So you see F's. And if you put your cursor on it, how I did for the website, see how it says -1 for the decimal, it's a sign value. So that way you don't have to like go and check. They already built all of that into the simulator, but you can use your programmer calculator to check. Other questions? Yeah, you have to set the value before you run it, okay? So set the value here, and then check your result at the above it. Yeah. If you run without putting the value, you have nothing. They're just empty variables. So there's nothing, no label doesn't have any value initialized. It will show you something there sometimes, but it's just because it's tied to addresses. But yeah, make sure you set the value. Okay, so let's look at, so take a screenshot of your simulator, right? After you identify your value at the locations in the register that load and store it, look at your LDI and STI, just like the last one. This is the same as the last question, right? So when I look at my program, I know that I loaded my label Y and Z to register 1 and register 2. And my Y and Z are tied to addresses here when I fill. So you can state that, right? Y is filled at, or is at location hex 3226. That's where you go to set the value. And then Z is at 3227. And then your X is loaded, right? Or it's stored from register 2, and it's located at hex 3225. And that's what the problem asks us to do. So talk about the register, the label, and the location for that question. B. So I put here, right? X is at, Y is so Y is loaded to register 1 and Z is loaded to register 2. And we fill, let me separate it. Okay. Any question? Let me change the font for this to show you that that was my answer. Okay, so let's do number 3, which is a little bit more complex than the last one, but not too hard. This one's easy too. So we are going to make a program. We have A plus B plus C minus 9 is equal to T. And you are going to do direct load. So same, we load to the label and it's given to you. A is located in this and it's using register 0. B is register 1 at this location. C is register 3 at this location and T is register 5 at this location. So we are required to use specific register. Add your comments to help you look at your code in the future or when you write through your code. Okay, so we are to take a screenshot and we are going to look at the location of T, and you should always check your value to make sure that your program is correct, right? That's the whole purpose in this. Okay, so I'm gonna go ahead and let me get my I think I labeled this exercise 2. Yeah, this is the one. Okay, 3, 5. Okay, so this is exercise 3. Let me resave it. So I know. Yeah. Okay. So we're gonna start the program with some comments. If you want, you can just put like this. So we're gonna comment out all the information that we need for the program. I like to put the requirements on the top for my comments so that way I don't have to go back and look at like what the program is supposed to do. So this is our equation. We have to fill these location and we're using these register. So start with the first line always is your origination address. So .org and put hex 3000. And then I'm using register 0, 1, 3, and 5 so I can clear those out. So here I clear register 0 by AND it with the 0 and put it back on register 0. Same thing with register 1, register 3, and register 5. So now after I have cleared the register, I want to think about how I'm going to declare my variable or load the label. Sorry, I wrote this with an LDI, but we're going to use LD as it's required. Okay, so after I had cleared my register for 0, 1, 3, and 5, and A is going to be at register 0, so I'm going to go ahead and load register 0 with A or to A. So A is loaded to register 0, and then B is going to load to register 1. Then remember the equation, it's A plus B in the parentheses, so we're working inside out. So we are now going to take A and plus B. That's easy. That's register 0 plus register 1, and I chose to put it back into register 1. So I'm reusing it. So register 1 at this point is going to hold A plus B by doing the add.
I had a question.
Yes.
I see the next one we're gonna load C to register 3. Could we do that before adding
Yeah,
Or do we have to do that after?
yeah. You can load everything up front. That's fine. Like how you do all your variable declaration at the top for C++, sure. That's really a developer choice though, right? Like for me, I load the label and I handle them and then I go to the next step. So it helps me track my program better. But if it's easy for you to do all the load at the top, that's fine. In my opinion, the way that I look at how I solve my problem is I do it by little, like one part at a time. So if I preloaded everything, I gotta go and look at, oh, which register I loaded to. So as I use it, I track my program better that way, because especially with the longer program, but if you like it, the other style, that's fine. I've had student that load and store, all the loaded at the top and then they store everything. If it's not required in other steps, they store everything at the end. So that's really, it's as long as you get the right result, it doesn't matter to me. And also, like, I chose to do it this way so you can see like what's used here being applied here. So C, I load C to register 3 because remember it tells us that here. Okay, loading C to register 3. Now the equation is A plus B plus C minus 9 inside the parentheses. So now we're going to handle the C minus 9. Okay. So in order to get 9 into the picture, I can skip a step by just adding 9 to this or subtracting it, but that creates some problem because if you skip something, sometimes it's not going to give you the right result. So the easiest way, the clearest way is to bring 9 to a register, because basically we are taking 9 and put it into a register and use that register to do the 2's complement and then add it to C, which is register 3. So I chose to use register 2, and I would take 2, I add 9 to it. Can you do a load 9 here? You can, right? But remember, load is just a read value for that register. So when you do a load, it's going to read 9 for register 2. In arithmetic calculation, remember that I need to take 9 and I need to bring the actual value in instead of its address or whatever. So I'm going to go ahead and add 9 to register 2 and then put it on register 2. So register 2, store hex 9. And then I'm going to do the 1's complement. And for the 1's complement of R2, I would not it, which is now it's not 9 at R2. And then I'm going to go ahead and do the 2's complement for register 2 because I just not it. So now I add the 1 to it and put it back on register 2. So our register 2 now have negative hex 9 or minus hex 9. And then our program requires us to use register 5 to store C minus 9, or register 5 is T. So what I did was I wanted to use T is C minus 9, and then I'm going to add this, right? So I would have register 5 is going to take C, which is from register 3, and then add the negative 9. So C minus 9 is now at register 5. C came from register 3 and negative 9 came from register 2. So I have this, and we're going to put the result to register 5. So that's only one portion. Then I'm going to add the A and B to it. And the A and B came from register 1, which is here. So I take register 1, which is A plus B, add it with C minus 9, which is in register 5, and then store the result back into register 5. And I'm going to do an ST here. So we can, instead of pointing to it, we can do a store register 5 to T, because that's our output. We're going to put it to a permanent address, which is labeled as T. After that, we're going to stop the program, and then we're going to do the fill. So A, we fill it at hex 3102. B, adjacent 3103. C, 3104, and T, 3105. And that's where you're going to go to set your value. Okay, and then check your result here. And then we can't forget the .n. Any question? So let me go and open my program. Let me change my load to, I like using LDI, indirect load. We'll talk about the benefits, or, ultimately you're going to get the same thing. Store load. Okay. We're going to go ahead and assemble the program. Check to see if it has 0 errors or not. Then we reinitialize our machine. We open our assembled program. We set our value. So I'm going to go ahead and use hex 3102. That's my A. And I can give it like a low value 1. The adjacent, which is B. 03. I'll give it a 2. And then for 04, oops, I'll give it a 7. And then click OK. And then run. And for those of you using the website, you saw how I did that earlier, right? Set your value before you run your program. And then you do the jump to. Or I can go a little bit before. Okay, a 1, 2, and a 7. Okay. Let's see, 3 plus. Let me rerun this code because I think I have a different code in my program there. Let's redo this. Any questions? So check your program, test it with the values, and then if there's discrepancy, you should go look at your code. Yeah, I had multiple files that I wrote. I'm trying to consolidate and make sure everything's correct there. Hopefully this comes from Word and it doesn't let me assemble this. Okay. Let me rerun this. $31.02. Oh, 4. Okay, we give it a number 4. Yeah, I'm off by 1. Let me check back on this. 2, 3 plus 7 minus 2. There should be 1. Five. C minus 9 plus B. Start back to T. Everything looks right. 3, 2 to 5. I'll come back to that. Okay, so tell me the location for T simulator. And then we'll do number 4. If we don't finish, I will push the last one to the next. But I wanted to do a control statement with you today too. Okay. I'll look at my code again. I think there might be a register that's off. Any question? Okay, so screenshot and then look at test your value. And then tell me the location for T. The purpose of these exercises is to show you how you can set value and test your program. That's basically the point in these. All right. So for this one, we are gonna work a little bit on the branches. Okay, and we'll come back to this in lecture quite a bit. We're gonna spend a number of weeks working through loops, while loop, for loop, if else statement. And so this is just the initial introduction. So we'll do 4 first, and then we'll talk about number 5. So in 4, just like what we've done in the last one, we have these variables P, Q, S, and Z. And they are all equal, right, up to S. So P is equal to Q, is equal to S, is equal to Z. And I want to add text for D. And as you look at the lab today, you saw my notes that if you're looking at the bit size right here, it's to the hexadecimal digits. That means that it's 4 bits plus 4 bits, that's 8 bits. We are going to have an overflow, okay? Because when you add your intermediate value, like decimal 1 or hexadecimal 9, it's only going to give you 5 bits to be able to do that. So it works perfectly with only 1 hex digit, but when you work with like 2 hex digit, it's going to have an overflow. So we are going to run into space limitations. So what we do is we're going to have to add this as 2 separate component, like 1 digit and another digit to make it equal to 4D. Okay, so that's how we're going to do that. Let me see. All right. This is actually pretty. Oh, I didn't really. Hold on. I don't think I wrote it to. Let me open it in the editor. Okay, I only did the other one, so I think I started this one with the other class. All right, so we can comment out, and I can write that right now. It's actually pretty easy. We're going to comment out our equation on what we needed, right? And then so we would start with origination address, and this is exercise 4. And then we are going to clear the register that we want to use. So we can pick any register. You can do 0, but in my case, I clear out register 1. And then I load that to the right. So I start from the right side and I can go left, because ultimately, if you can have 1 register to do this, and then you just store it to the label continuously. So it's really easy. Okay. So we clear out the register, and then we're going to load Z, which is this part that I highlighted, to register 1. So I'm going to do an LD or an LDI. Let's do an LDI to register 1. Then what we can do is we can add this in 2 parts, okay? Because if you add hex 4D like this, it's gonna throw an error because it's gonna say that this is too large, okay? So the easiest way to really look at this is if we have a hex 4D, right? If we subtract hex 4, right? You have a 4, 9. So what you want is you want to be able to think about like how you can break it down into subpart where it's going to fit 5 bits. And it could not just be 2 steps. It might be 3 steps, and you can do it that way. Okay, so let's say 4D. Let's see if I do minus hex D, right? I would have a 4, 0. So I can do a hex 4, 0. So what you want to do here is you can say we can do a hex 4, 0, but you got to check to see, is hex 4, 0 going to fit into the 5 bits? Now, if we shift this down to a byte or even half of that, you're still going to have the 2 digits. So you have to break it down to the subpart. So I'm only going to be able to start this for you because I got to explain the next part, okay? So let's say that if I add, let's do the D first. So R1 is equal to hex D. And then I gotta add the next part, right? R1, and then the next value. So we can think about what else can we add to make it smaller, right? So if I take this and let's say that if I subtract, let's see, 4, 6 equal to decimal 64. So right now I'm still at 2, 4, 6, 7 for 7 bits. So I got to take it down 2 bits to be able to do that. So let's see if this is on, this is on. So if I do F, then I have R1 is equal to hex D plus F, and we can check, right? So if I do D plus F, that's 42, and then subtract hex 4D. The difference is we're gonna do a 5. So add R1, and hex 5. So at this point, R1 is equal to hex 4D. And that's how you do that. So this 3-step right here, or actually, yeah, 4 steps right here is just this part. But everything else is easy after that, right? So let's say that if you want to have like separate register for like S, Q, and P, that's gonna be really easy. We can say, let's say that if I want to load register 2 as S, load S to R2, and I can do the next load so you can see. Oh. Okay, so if I want to make Z is equal to this, I can do a copy. And add R2, R1. X 0. So R2 is S, which is equal to Z plus 4D. Okay, so what I did was I load the label S to register 2. And I have to represent S, right, as another register. And so if I want to copy the content of register 1, I simply add it with the 0 and I put it onto register 2. So register 2 already has S as what we saw here. And we take the content of the register 1, which is your Z plus 4D, okay, and put it onto register 2, which is S. Now we just do the same thing to, now you can just skip this part and you can load and store. But what I want to do is I can show you that we can make this equal, right? So we can do an LDI R3 that's equal to Q. And we can do the same thing, load Q to R3. And then we can do an add R3 is R2 hex 0. So R3 is equal to S is equal to Z plus hex 4D. And then we can do the same thing with the next one. Q. Oh, sorry. What was it? P. R4 is equal to P is equal to S is equal to Z plus 4D hex 4D. I forgot the Q. So now if I want to check my answer, I can do an STI R4 to actually, I apologize. This is not, you don't need this. We're gonna do an STI to R3 to Q to P. Okay, let me explain. So at this point, you have this, right? You have Q is equal to S is equal to Z plus 4D, hex 4D. And then we know that P is equal to this, so we can store it to P. Now you can skip all of this and you can store it earlier. I could actually store it as soon as I got this part instead of doing this, right? I can store it to S, I can store it to Q, I can store it to P, because all my operation needs to be is I need to take the Z plus hex 4D, right? This is the important part right here. So once you have the result in that, whatever the register is, you can store it to the label S, the Q, and the P. Okay, you don't have to do the extra load. I really feel like the extra load is not necessary. Okay, so I'm gonna bold this or highlight this. So if I can store it to P, STI R3, I can store it to Q, STI R3, I can store it back to, because it's the same exact value, to S. And then I can do a dot fill. And I can halt here. And then I can do P dot fill, right? You can say hex, you can give it like 3200 or something like that. Q dot fill hex 3201. S dot fill hex 3202.
I don't think you can use register 3, can you, to store it?
Oh yeah, because you can store it to, it's the same, or you can copy. It should be able to store it. Because it's the same exact value. The value here doesn't go away until it gets here.
Oh, okay.
Yeah. So because remember that this is equal to this equal to this is equal to this, right? So we just need to operate the arithmetic calculation for this, and we can store it to this label, and this label. It's just like you saying variable 1 is equal to variable 2 is equal to variable 3 is this, right? Z plus hex 4D. So you just need to operate this, and then you can store it to separate label. Basically, I point to the addresses that stores the same value, right? I store the same value to these addresses. That's what I'm doing. Oh, I'm sorry, not register 3, register 1.
Yeah, so
Yeah, that's what you were saying. I thought you meant. Yeah, register 1. I forgot that I took this out. Let's take this out. We don't need that because it's extra step that's not needed. It's extra process that we don't need. Yes, you can load and store, but that's just like redeclaring a variable that's storing the same thing instead of reassigning the variable for that same value. So, and then don't forget the .n. Okay, so let me zoom out. All right. So what we did, yeah, question?
Are we adding everything into R1? Does that mean like Z is equal to X4D rather than Z plus X4D?
No, yeah. So you can't think of it like Z is equal, right? Because basically you're saying that register 1 holds Z here.
Uh-huh.
And then you take Z, you add XD, XF, X5, so it's Z plus X4D. But you put it back into register 1. So register 1 is a file that holds Z plus X4D, right? Originally it held Z, but then you add more component to it. So basically it's saying that it points to the location of Z, and then that location we're gonna add the value. You understand?
Yeah.
It's not actually Z equal. Because if you think of it, the way that I put this on here is I don't want to say Z is equal to R1 is because that can be confusing, right? You're just saying that R1 point to Z, where we go take that and we're going to go ahead and add it.
Okay.
Okay. And then once we get here, once we have the added hex 4D, then we are going to, as long as it's not overflowing, otherwise you're going to get inaccurate result. We're going to store it to all of these other labels, P, Q, S, and then we fill them. You guys are the first class that I actually finished this one with, because usually I just start it to where they get here and then they have to add the rest. But you get now how we can load to one and we can also store to other location. So basically it's using the register to point to like multiple location in the memory because they are the same value, or they have the same value in the container. And then I forgot the Z here. Sorry about that. And you can be cleaner with the code in like the order of your addresses, like based on the equation. So I would start with Z at first and then, you know, the output later in the address. So it's easier to check, but just make sure that you look at the address when you set the value. So that makes more sense. But I'm just trying to do it quickly so I can get through the next program. I'm mostly going to explain it to you because that way you understand the branching. Any question? So this is the exercise 4. Yeah.
How did we get to hexadecimal 4D?
Yeah, so hex 4D, this is 8 bits, right? So in your instruction, in your word size, this takes already up 4 bits, right? And this is the remain, but we have to reserve like a couple of bits for the flag. So the value here has to fit into the 5 bits. So why can't I add the hex 4D here is because when it's 2-digit, it's 8 bits. It's overflowing. So what I do is I have to chunk it up into multiple processes to add that value. So that way I can fit, 5 bits or 4 bits, 4 bits and 4 bits here. Okay. So I take the hex 4D, and you don't have to add it with D first. I basically take 4D, subtract D, and I have what's the difference. And then I add the next part and the next part. So basically this is broken into 3 individual digits to make it a hex 4D. And the best way to do this is to use your calculator. And that's what I did, right? I take hex 4D. I subtract D, right? I have 40. And then I decided that the maximum number of, when all the 5 bits are turned on, it's F. Or the 4 bits are turned on, it's F. That's at the end of your hex value set, right? So I would take that and then I subtract F, which is 31. And then you would keep on going. Okay. So I think I'm also missing another step, but you have to, the point here is to take this and break it into multiple steps until you get to hex 40. So hex 5, and then so hex 31. And when you look at this, 31 is still, right? If we look at the binary, it's still this many bits. You have to make sure that it's under 5. So I can't just go add R1 hex 30, right? It's that I have to fill, I can fill and be able to do that. But when I add, I have to add something that's smaller. So let me redo my calculation here because I think I'm missing. So that will be D plus F plus 5 equals 21, right? And we still have 21 subtract hex 4D. Okay, you still have D4, so you have to keep on going. Okay, so I'm gonna put that here. Let me give you a complete program here. Where were we? 21. So if we keep subtracting, so that's a 5. Let's say if we do an F here. So D plus F 2B. Okay, got it. So we need another F. Let me pull this up. 9 minus 40, and then we need another C. Okay, that's complete. So we add D, F, 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 C. And you guys can check me on our calculation. So sometime I did it in a hurry. I might punch in the wrong thing, but this should be 4D and then store it out. Okay. And that's how you're able to handle things that are larger than 5 bits. So when you have 2 hex digits, that's 8 bits, and 8 bits needs to be like this. Or depending on the values, that is. Okay, other questions? All right. Okay, so screenshot, note the location for Z. For question C, it says, based on your observation and the simulation of the program, compare and contrast this exercise to the previous, or contrast this program to exercise to the prior exercise, that should say. Instruction, addressing, and execution. So if we take this program and compare it to the last program, right? This program requires us to do the multiple step for this part. And we can also store from the same register to many labels. And that was what we see in this code compared to the prior, right? So it's really the requirement of the arithmetic calculation inside the program that is going to give us the sub-steps in how we write the instruction for our assembly language, okay? And we're still going to use address in the field. That's where we're going to go be able to set our values and check if our output is correct, okay? Any questions?
Just to clarify what you said earlier,
Mhm.
the program requires multiple steps or hexadecimal for D and can use the same address for P, Q, and S.
Mhm.
All right, that's all.
Yeah, so you can use the same, yeah, you can store from the register to other label that uses different address, but the address here, you can pick and choose any location that's after your program, okay, after the hex 3000. And we want to give it space, so you can do 3100 or whatever you like. But yeah, 4D, because it's 2-digit, it has to be broken up into many steps. And this requires you to look at the arithmetic calculation for hexadecimal. So I use the calculator and I start with 4D and I subtract a value that's going to be added here. Subtract another value. And the easiest is to look at F. That's when all the 4 bits are on, right? F. And so we would have these. All right, I'm almost out of time, so I want to spend a little bit of time talking about the next program because you can copy and paste the code and you also see the comment from my screenshot. So for this question 5, right? Or number 5 basically tells you about branch and the label, okay? So branch is a direct branching. So when you can have a BR without any kind of flag, right? When you need to send it to that location, it'll just branch to that location. So for example, instead of jump, I can do an unconditional branch. That means that it doesn't need to check whether it's negative, 0, or positive. Okay, N for the negative bit, 0 for the 0 bits, and P for the positive bits. So what we want is it's gonna, based on the previous line, it's gonna check for that bit to be either positive, 0, or negative, right? We can do an RET for return, and return specifically use the value from register 7. So when you do a function, when you do a return, let's say that I have a function to calculate sum, and I'm going to return from that function. That sum is going to, and in assembly, we call this subroutine, like Java. You use the value in register 7 as the base address for your return. So it's going to store to that location, and R7 is going to point to the return value, and that's what it is. So when we return, it does a jump R7. So it's going to go to R7, and R7 has the address of your return value. So when you have an RET, that's what happens in the back. Okay. Now, for JSR, we're going to spend a couple of weeks on this more. So this is just a preview. JSR is an instruction that puts the address of the next instruction after it does the jump for subroutine. This is used for function call. Okay. The reason why it puts the next address or the address of the next instruction on there is if you notice that when you, let's say I have 3 functions. If I call the first function, right, at the end of that function call, when it returns a value, it's going to go to the next function. So what's going to happen is your program counter is going to utilize, right, the address of the next subroutine to be able to move forward in the program. So this is going to allow it to be able to jump to the function or to jump to the subroutine. And it's also going to use register 7 to keep the address so that way it would know where to go. Okay. And the way that we write the function is to use a label, just basically a name on the left. So let's say that if I have a function call sum or make sum, right? And then I would just have a label called make sum, and I would use the JSR to call the function by saying JSR make sum. And then I define the function in that label section. Okay. So in this one, what you see is here we have a compare label. All right. So let's do the rundown for this real quick. And you can run the program, after you input it in. It is a little longer. All right. So you are clearing the register here at the first 2 lines after your origination address. Clear register 1 and register 2. You are going to load a reset label to register 6. And because you're working with string, you are going to do a load effective address to register 0. Remember, this is for output and input, right? So we're going to load the effective address to register 0. It's specifically for in and out. And we're going to use the label called line 1. So the address of the line 1 string is going to go to the register 0. And right after you load the effective address, you want to output it. So you're going to do a put. This is a pseudo instruction. We saw this during the 2nd week. Okay, so it's going to display the text or the string in line 1 on console. And we're going to ask the user to do an input. So basically, I'm doing a prompt. I'm asking the user to enter some kind of value, right? So I have to do a cout here, which is like a load effective address for the string, and then display it. And then wait for the keyboard. So here it's only going to wait for 1 character input. So instead of using in, I'm using a get C here. So it's going to read input of 1 character, and then it's going to show the input by doing an out. So when I do an out here, it's going to show what the user entered. And basically, it's going to pull that from register 0. So it got it from register 0, and it's going to take that register 0 and then display it, right? And then at this point, I'm going to ASCII convert. So before I ASCII convert, I'm going to make sure that I fill my ASCII with something. So we'll talk about that. So here, when you take register 6, which is the reset label, you're going to add it with register 0, which is your input. And then we're going to put it on register 1. Okay, because we cleared that earlier. So whatever that's in register 6, add it with the input and store it into register 1, because we have to, when text comes in, we have to ASCII convert now. Okay. And register 6 is gonna help us convert that. And then we do the same thing for line 2, another message to ask the user to do a second input and then display their input. So 2 input, input 1 and input 2. And as we take the input, we have to ASCII convert right away. Otherwise, the second input is going to override it. So you have to do ASCII conversion here for the first input and then the second input. Got that? Now we're going to call the function. We're going to do jump to subroutine compare. So as we call here, we're going to define our function below. Okay. So when you need to do a function call, you do a JSR and then its label. And after the function call, this is halt. So think of this part is main in C++. Right? And you prototype your function at the top and then you have the function definition. So here's your function definition. This is your compare function. We clear register 3. We're going to do the complement for the 2. So the register 2. Why register 2? It's because we are going to subtract. We are going to take the first input, subtract the second input. So that's why we have to do the 2's complement because we're getting ready to subtract. Okay, so we're going to ask the user to enter one number, another number, take those number and subtract. And we're going to check whether it's positive or negative, and we're going to display that. Okay, so this is for the subtraction. Now here is where you branch. So you do a BRN. Here is where you check if it's negative. And when it's negative, when you add it with 0 for copy, so the output for the subtraction is in register 3. It's going to go here to this register to check to see if it's negative. If that's true, right, it's going to output that it is negative. So it's going to add, it's going to execute this body. Add R3, it's going to copy the result to register 3. Now, if R3 content is positive, right, it's also going to do the same thing. So it's going to execute this right here. If it's 0, it's going to go to EQ. So if it's negative, it's going to go to this section called negative, right, which is here. And if it's positive, it's going to go here. If it's equal, it's going to go here. Get it? So this is why this is a way that we can control the flow of the program. When it branch for negative, it's going to go to negative section and then copy. When it's positive, it's going to go here. It's going to do this and then copy. And then when it's equal, it's going to go to EQ, do this, and then copy. Copy. And then do the R5 copy. Okay. Or clear R5, I should say. So in the negative section, it's going to trigger, right, the N, which is a string. It says less than. P, it's going to trigger the string greater than for positive. And for when it's equal to 0, it say X is equal to Y. Okay. And for the reset, we are going to fill it with FFD0. This is, as we talked about in the second week, this is -30 for ASCII conversion. Because we have to subtract it when it first come in, right? And then, you know, we're not outputting the value, so we don't have to add it back. We just need to subtract it to make it a hex value and then check for the condition. Okay. So this is an X minus Y program. And basically we're checking to see if X is greater, less than, or equal to Y by doing subtraction. So once you build the program, what you will do is, I'm coming close to the hour now, or the minute now that I have to finish up, but we can go a few minutes. Let me reinitialize the machine, open this, open 6. And then I don't have to set anything. This is going to run on the console with input and output. So I'm just going to go ahead and do this. Make sure you guys check your syntax when you write up the program. So it asked me to enter text, right? And that comes from this line 1. That's the LEA inputs. Okay. So let's say I put in a 2. And then it asked me to enter Y. That's the line 2. That's the LEA for the Y input, right? So let's say that I put in 4. And so 2 subtract 4, it would say X is less than Y. Now, just like before, I said that no program is perfect. There is also limitation to this program. So when you test your input, right, it works really well with the smaller numbers. Because it's only one character. That's one of the limitation. And so there is limitation in how this program is written as well. But here you can see how a function is used and how we can call a function, and we can use if else statement here. If X is greater than Y, then show X is greater than Y after we subtract. Okay. And the program continues to run, so make sure that when you're done, you can stop it by clicking the X, or you can hold. So it's going to keep running. Any question? So take a screenshot for exercise 6 after you write and run the program. Test it with the input, of course. And then look at the program, how it's written. How would you improve this program, right? With what you've learned so far, what we talked about with branching, is there a better way? There's so many ways that you can do comparison type of program. X is X greater than Y, right? Is X less than or equal to Y? Is there a better way to do this as far as improvement? And that's what you need to answer for this question. Do your best. All right, any question? Okay, let me stop recording.